Imagine a world where this fundamental process involves iron instead. WASP 76b sits 637 light-years away in the constellation Pisces, making it practically our cosmic neighbor in the vastness of our galaxy. This exoplanet belongs to a category we call gas giants, similar in some ways to Jupiter in our solar system. But that's where the similarities largely end. While Jupiter orbits at a comfortable distance from our Sun, WASP 76b breaks all conventional rules about where and how planets should exist. Scientists classify WASP 76b as an ultra-hot Jupiter, a term that hints at just how extreme this world really is. These planets represent a class of gas giants that orbit shockingly close to their parent stars. When astronomers first discovered planets like this, they had to reconsider everything they thought they understood about planetary formation and evolution. These worlds simply shouldn't exist according to our previous models, yet there they are, defying expectations. The orbital mechanics of WASP 76b showcase its extremity. This massive planet completes an entire orbit around its star in just 1.8 Earth days. For comparison, Earth takes 365 days to circle the Sun, while Mercury, our solar system speedster, requires 88 days, making WASP 76b nearly 50 times faster than Mercury. This rapid orbit places the planet incredibly close to its star, only about 3 million miles compared to Earth's 93 million mile distance from our Sun. If we placed Earth that close to our Sun, our planet would be inside Mercury's orbit. This extreme proximity creates conditions unlike anything in our solar system and sets the stage for the planet's extraordinary weather phenomena. The close orbit triggers powerful gravitational forces that have tidally locked WASP 76b to its star. Like the moon always showing Earth the same face, this planet permanently presents one hemisphere to its star. This creates two distinct realms divided by a stark boundary, a perpetually scorched day side facing the blistering star and a permanent night side that never receives direct starlight. The contrast between these hemispheres creates the most dramatic environmental divide ever observed on a planet. The day side exists in a perpetual state of scorching heat, while the night side, though still extremely hot by Earth standards, remains significantly cooler than its sunlit counterpart. This temperature gradient drives atmospheric dynamics that lead to the planet's most famous feature. This permanent day-night division creates perfect conditions for extraordinary weather. On the scorching day side, temperatures soar high enough to vaporize iron, transforming solid metal into gas. This metal vapor gets caught in atmospheric winds that carry it toward the cooler night side. As the iron vapor crosses the boundary between day and night, it cools rapidly and condenses into liquid droplets that fall from the sky as metallic rain. On Earth, our rain consists of water droplets that nourish our planet and sustain life. On WASP 76b, the precipitation consists of molten iron droplets falling through an atmosphere laden with vaporized metals, a weather forecast that defies our earthly understanding of planetary systems. When scientists first proposed the iron rain model, it represented such an extreme concept that many researchers approached it with healthy skepticism. However, subsequent observations have provided compelling evidence that this bizarre phenomenon actually occurs. The implications stretch beyond this single planet, suggesting that metal weather might be common on ultra-hot worlds throughout our galaxy. This discovery reshapes our understanding of what constitutes weather on alien worlds. On Earth, weather involves the cycling of water, air masses of different temperatures, and occasionally solids like hail or snow. But WASP 76b shows us that planetary weather systems can involve elements that remain firmly solid on our world. The iron rain cycle on WASP 76b mirrors Earth's water cycle but with dramatically different materials. Where Earth has oceans providing water for evaporation, WASP 76b likely has areas where liquid iron accumulates. Iron vapor fills its skies instead of water vapor, and iron precipitation cascades through its atmosphere instead of water droplets. This cycle creates a perpetual loop of extreme conditions. The day side vaporizes iron. Atmospheric circulation carries this vapor to the night side. The vapor condenses into liquid droplets. These droplets fall as rain, and eventually, through the planet's circulation patterns, this material returns to the day side to repeat the process. The iron rain probably doesn't fall uniformly across the planet's night side. The boundary between day and night, what astronomers call the terminator line, likely experiences the most dramatic precipitation, creating a band of intense iron rainfall circling the planet at the edge of perpetual darkness. The physics involves more than just temperature. Pressure changes throughout the atmosphere also play a critical role in determining where and how the iron condenses. Just as water on Earth exists as vapor, liquid, or ice depending on conditions, iron on WASP 76b transitions between states based on local atmospheric conditions. This reframes how we think about familiar elements. On Earth, iron represents strength and solidity. We build structures, vehicles, and tools from this robust metal. On WASP 76b, this same element behaves more like water does on our world, flowing, evaporating, condensing, and falling from the sky. It's a profound reminder that the properties of materials we take for granted depend entirely on their environment. But to truly understand why metal falls from the sky on this bizarre world, we need to grasp just how hot this hellish planet really is. The temperatures on